Another one more unit in the CSR point of view or another examinations point of view, electrochemistry. Electrochemistry, which is mentioned in the syllabus point of view, starts with the Nernst equation and electrolytic cells, like that it may be continuation takes place. So what it may be generally we know that electrochemistry, that means the conversion of energy or the branch of chemistry. Electrochemistry is what? The branch of chemistry for the conversion of chemical energy to the electrical energy, or vice versa, reverse takes place, electrical energy to the chemical energy. Well, reactions takes place, that is converted to the electrical energy, or it may be by passing through the current like that. So by passage of the current, it may be reactions takes place. So conversion of electrical energy to the chemical energy or chemical to the electrical energy, that it may be generally considered. So it may be number of forms it may be there, but we consider like that. So in this electrochemistry point of view, right, first we know that some of the terminologies before we go to the Nernst equation. Electrolyte is what, and strong electrolyte, weak electrolyte, some fundamental definitions about that. So not going to detailed discussion, but fundamentals. Strong electrolyte is what, weak electrolyte is what, electrode potential is what, because we are using the Nernst equation electrode potentials, right? EMF which we are calculating takes place, right? So in the electrolyte is what? If it is a substance, right? So the substance, if it is a substance, this allows the, when the substance allows the passage of electric current, the substance allows the passage of electric current through it. If it is a substance, either it may be the solution, that solution it may be in the molten state or it may be fused state, whatever it may be, that it may be there. The substance which is present in the molten state, or it may be the fusion state, or it may be the solution state, whatever it may be there. So this substance, if it is allows the passage of electric current through it, this particular substance is called as the electrolyte. If it is allows the passage of electric current, that particular one is considered as the electrolyte. And this electrolytes, it may be further strong electrolytes are there and weak electrolytes are there. Strong electrolytes and weak electrolytes are there. This particular concept I can explain again in the ionic equilibria case. In detailed discussion also we have seen, but generalized case I can explain the strong electrolytes. In the case of the strong electrolytes, whatever the electrolytes which allows the passage of electric current through it, that is considered as an electrolyte. That electrolyte, right, that electrolyte in strong electrolytes, the electrolyte which is going to be complete dissociation takes place or nearly complete dissociation takes place, or approximately complete dissociation, or near to the complete dissociation, or complete dissociation takes place, complete dissociation takes place. Complete dissociation, if it is, suppose if it is HCl is there, 100 molecules of HCl, 100 H plus ions, 100 Cl minus ions, or if it is there, or 95 or nearly complete ionization or near to the complete ionization takes place, that substance is which is called as the strong electrolytes. Complete ionization takes place, or complete dissociation or complete ionization takes place, that substance is called as the strong electrolytes. And the weak electrolytes are the substance which are going to be partially ionized or partially dissociation takes place. Partial dissociation takes place. Partial dissociation takes place or partial ionization takes place. Partial dissociation or partial ionization takes place. That substance is that electrolytes which is called as the weak electrolytes. That means if it is suppose acetic acid, that is the weak acid, is considered as the, so the examples of the weak electrolytes are weak acids and weak bases. Weak acids and weak bases is considered as the weak electrolytes. Suppose acetic acid is a weak acid, acetic acid is a weak acid, and ammonium hydroxide NH4OH is a weak base, like that it may be there. Suppose if it is weak acid, acetic acid if it is there, Suppose 100 molecules of acetic acid is there, 100 molecules is there. Suppose if it is going to be dissociation takes place, right, CH3CO minus H plus, only 30 or 40 it may be going to be dissociation takes place, remaining 70 it may be in the molecular form. Remaining 70 it may be the molecular form. If it is in strong electrolytes, suppose, which one is the examples of the strong electrolytes? The strong acids and strong bases. Strong acids, strong bases, and some of the salts which came from the strong acid as well as the strong base, like NaCl. That it may be salt, it may be came from the NaOH and HCl. That it may be the strong base as well as the strong acid. So strong acid is HCl and strong base is suppose NaOH, like this. So this NaOH or HCl, which is strong electrolytes, right, that it may be complete ionization takes place or nearly complete ionization takes place. So that means the ions it may be there in the after dissociation takes place, that it may be more number or approximately equal to the how many number of molecules are there. That means it may be their degree of dissociation, which is considered as an approximately 100%. The degree of dissociation it may be the 100% or unity. 100% or unity. In percentage form 100% or unity. And here in this case the degree of dissociation is less than 100% or less than 1. That it may be not 100% because these weak electrolytes are not complete ionization takes place, right? So strong electrolytes and weak electrolytes, right? Strong acid, strong bases, and some of the salts which came from the strong acid and strong bases. And here it is weak acids, weak bases is examples, or some of the salts which came from the weak acid by the combination of the weak acid, weak base. Suppose these two are NH4Cl if it is there, NH4OH, and some of the I can explain later in the case of the ionic equilibria case and sparingly soluble salts case. I can explain that salt which came from the weak acids, weak bases, that it may be considered as also weak electrolytes. Next, another one fundamental before we are going to discuss the topic, electrode potential. This is important. Electrode potential. Electrode potential. What is an electrode potential? Electrode potential. E or EMF. E. So we can consider the electrode potential. Electrode potential. If a rod, right, or a metal or a metal rod or a metal plate, like that, metal rod or metal plate. So if a metal is dissolved in the or is dipped in a solution of the electrolyte solution, if a metal is dissolved in the or dipped in the is a metal rod or metal dipped in the solution of its electrolyte solution of its electrolytes. Solution of its electrolyte. Metal is dipped in its solution of its electrolyte. What will happen when metal is dipped in the solution of its electrolyte? Then around that metal is contact with the solution. That metal is in the contact with the electrolyte solution. So at the metal rod position, due to the charge separation, electric double layer will be generated. Electric double layer is generated. So the electric double layer is generated between the metal rod as well as the electrolyte solution. So at the end of the electrodes, so at the electrode position, so electric double layer is generated. The charge separation, like plus minus, the charge separation or electric double layer is generated. Due to the generated of the due to the developing of the electric double layer, some potential will be developed between the electrode as well as the electrolyte solution. Some potential difference is there. So that will be recorded as the electrode potential. At electrode position, some potential will be developed due to the electric double layer. That potential which is called as the electrode potential. Electrode potential. If a metal, if it is there, if a solution is there, this is a solution, right? So electrolyte solution, if a metal is dipped in the electrolyte solution, right? So here it is, electric double layer is generated, that means charge separation is generated. That electric double layer is generated. Due to this electric double layer, some potential will be developed. That potential is considered as the electrode potential. At electrode position, potential will be developed. That is electrode potential due to the electric double layer. Now, that means if it is, I mentioned that the metal rod is dipped in the solution of its electrolyte. Solution of its electrolyte. Suppose if it is zinc rod which is there, is dipped in the zinc sulfate solution. Zinc sulfate solution. If it is copper rod is there, that it may be dipped in the copper sulfate solution. The zinc which is act as zinc rod which is act as electrode, and copper rod also which is act as electrode in the copper sulfate solution. That means whatever the metal, if it is taken, is dipped in the solution of the electrolytes or solution of its ions of the electrolyte. Solution of its ions of the electrolyte means if zinc rod is dipped, suppose in that solution zinc plus 2 ions are there. So zinc rod is dipped in which solution? Zinc sulfate. This is an electrode, zinc electrode is there. Zinc rod is dipped in the zinc sulfate, suppose. That means which one is considered, zinc sulfate means which one is the, when it is going to be dissociation takes place, zinc plus 2 and SO4 minus 2, Zn plus 2 ions are there. So whatever that the metal, if it is taken, suppose the metal, if it is dissolved in the solution, electrolyte solution of its own ions, zinc plus 2. Suppose if it is copper rod which is there, which is dissolved in the solution of which solution? Copper sulfate. In the copper sulfate, which one ions are there? Cu plus 2 ions, SO4 minus 2 ions are there. So the copper rod which is dipped in the solution of its own ions. Solution of its own ions. When what will happen? Solution of its own ions will be taken, some potential will be developed, that potential will be an electrode potential due to the generation of the electric double layer. Charge can be delivered, takes place like that. Now, which one is considered as an oxidation potential, which one is considered as the reduction potential now? Which one is considered as oxidation, which one is considered as reduction potential, because that is also important further point of view. The oxidation potential. Oxidation potential. Oxidation. Oxidation potential is what? This is an electrode potential. Now, the potential will be developed. Potential develops at the electrode. Potential develops at the electrode due to the oxidation process. Due to the oxidation process. If potential is developed at the electrode due to the oxidation process, that potential is called as which one? Oxidation potential. That potential is oxidation potential. Or the tendency of the electrode to lose the electrons. Tendency of the electrode to lose the electrons. The tendency of the electrode to lose the electron, that is considered as an oxidation process. That potential is considered as an oxidation potential. The tendency of the electrode to lose the electrons, or during the oxidation process, the electrode potential is oxidation potential, or the tendency of the electrode to lose the electron. When losing the electron, that it may be considered as, or loss of the electron, it is considered as which one? Oxidation process again. So suppose if it is the metal, like that it may be there in the solution, like that electrolyte solution, M is the metal suppose. The tendency of the electrode to lose the electrons, M plus 2, suppose 2 electrons which is there, or M plus N if it is losing the N electrons, there's a loss of the N electrons. This process is called as which process? Oxidation process. This process, oxidation process. Loss of electrons is considered as an oxidation process. During this process, the developed potential is called as which one? Oxidation potential. During this process, the developed potential is oxidation potential. Now, this oxidation potential of this process, how can you show that the oxidation potential? When metal is going to be M plus N, metal is changed to the M plus N, while losing how many electrons? N number of electrons, which is losing takes place. While losing or loss of N number of electrons, this will be happen. Right? That means metal is going to be, what will be happen? Metal is going to be M plus N. Metal is going to be M plus N. This meaning is what? This meaning is oxidation. This meaning is oxidation. When this meaning is oxidation means metal is, which one it may be takes place? By the loss of N number of electrons, this will be happen. Right? So this meaning is what? Metal is changed to the M plus N. That means by losing the electrons, M plus N will be there, charge is there. So this process is called as which one? Oxidation. This process is called as oxidation. Now, which one is the oxidation potential? The oxidation potential is the electrode potential like this. During the oxidation process is what? M is going to be M plus N. This is considered as which one? Oxidation potential. Oxidation potential, E oxidation is what? M is going to be M plus N. Suppose in a Daniell cell, zinc is going to be zinc plus 2 while releasing the 2 electrons. This process is which process? Oxidation process. This process, oxidation process, while losing the 2 electrons. Now this process and oxidation process, the electrode potential, so this what will happen here in this case? Zinc is going to be zinc plus 2. This is an indication of the oxidation process. So oxidation potential is what? E of zinc is going to be zinc plus 2. Oxidation potential. Right. Next, reduction potential is what? Next, another one is reduction potential. You know that oxidation potential, you know that reduction potential, then only you can calculate the total E cell. Because oxidation is happened and reduction is happened. That means it is act as anode, act as cathode, it may be there. 2 electrodes which is there. One is at anode, another one is at cathode. At which position, which one reaction will be takes place, I can explain. This is a fundamentals one. You go through the Nernst equation. Before that, these some fundamentals it is required. I can explain within 1 hour like that. So this is an oxidation potential. And what is reduction potential? What is reduction potential? E reduction. I can explain in the earlier one. The potential is developed due to at the electrode during the oxidation process, oxidation potential. Now the potential is developed at which one? Electrode. Which process? During the reduction process. During the reduction process, that is called as the which one? Reduction potential. During the reduction process, the potential developed is reduction potential, or the tendency of the electrode to lose the electrons. That is called as oxidation process. To lose the electrons, that is called as oxidation potential. Or here in this case, the tendency of the electrode to gain the electrons. Is called as the reduction potential. The tendency of the electrode to gain the electron. To gain the electrons means which one? That process is the reduction process. Again, reduction process developed potential is reduction potential. To gain the electrons, that means here it is, suppose M plus N is there. While taking that N number of electrons is deposited as the metal solid like this, M solid. Right? So here it is also like this, M solid. M plus N like that. So this process is which one it may be takes place while receiving the electrons, right? N number of electrons. So this process is called as which one process? Reduction process. You know that familiar one. This is reduction process. In the reduction process, what will happen? Metal M plus N will going to be which one? M. How it will be takes? While N number of electrons. Like in this earlier one is while losing the N number of electrons, right? This it may be takes place, and here in this case, while receiving the N number of electrons, it may be deposited, the charge, it may be neutralization takes place and deposited as the neutral solid, like that. So charge can be neutralized while receiving the N number of electrons. and here in this case it maybe takes place while losing the n number of electrons. Now m plus n is going to be which one? M plus n is going to be m. How? While receiving the n number of electrons. Receiving the n number of electrons. This process is called as which one? Reduction process. Metal m plus n is going to be m. This is called as reduction process. The reduction potential can be shown E of m plus n is going to be m. This potential is considered as an which one? A reduction potential symbol. The symbol of the reduction potential. Right? In the earlier one is which one? This is oxidation potential. Metal is going to be m plus n while losing the n number of electrons. Here it is gaining the electrons. This is maybe happen. Reduction potential. Right? Suppose I can give in the Daniell cell in the right side Cu plus 2 copper electrode is there, so like that Cu plus 2 electrolyte solution, while taking the 2 electrons and deposited as neutral copper and like solid. So this it may be considered as which process? Reduction process. This while receiving the electrons, you know that this process is reduction process. And reduction potential is what? Cu plus 2 is going to be Cu. This potential is called as which one? Reduction potential. Cu plus 2 is going to be Cu. This is called as reduction potential. Now, the conversion of the oxidation potential to the reduction potential is possible, and reduction potential to the oxidation potential is also possible. Conversion of reduction to oxidation and oxidation to reduction potential is also possible. So, if it is oxidation potential is there, this one is their oxidation potential, is converted to the reduction potential, how? By putting the minus charge. Or reduction potential is converted to the oxidation potential also by putting the minus charge. Suppose if it is reduction potential is there, this reduction potential value is converted to the oxidation potential by putting the minus charge before that reduction potential. Minus of reduction potential is oxidation. If it is oxidation potential is there, that will be converted to the reduction potential by putting the minus charge. This it may be converted to the reduction potential. Right? So I can explain one example like this. In the explain like that, zinc is going to be zinc plus 2 electrons. This process is called as an oxidation process, or I can explain directly E of or E0 of the standard electrode potential. I can explain what is standard electrode potential later. Or in that format I can explain standard electrode potential case. Suppose the oxidation potential is converted to reduction potential, or reduction potential is converted to the oxidation potential. How? By putting the minus sign before that. Right? And here another one more I can explain. The standard reduction potential is there. What is standard reduction potential? Standard reduction potential. So the standard reduction potential is, how can you determine the standard reduction potential? What is standard reduction potential? The electrode potential, if it is measured, at 25 degrees centigrade, which means like that 298 Kelvin, 25 degrees centigrade, and 1 atmosphere pressure, 25 degrees centigrade as well as 1 atmosphere pressure. The electrode potential is measured at 25 degrees centigrade and 1 atmosphere pressure is called as standard electrode potential. Standard electrode potential. Standard electrode potential E0. That can be shown like that, E0, standard potential. Like the standard Gibbs free energy, standard entropy, and all it may be, we are using that E0, standard conditions. And generalized case, all standard conditions case, either it may be Helmholtz free energy and Gibbs free energy, like earlier one in the thermodynamics, like that. Here it is also the electrode potential, if it is measured, electrode potential, this electrode potential is measured at which one conditions? 1 atmosphere pressure and 25 degrees centigrade temperature. 1 atmosphere pressure and 25 degrees centigrade pressure. The electrode potential, if it is measured, that electrode potential is called as the standard electrode potential, E0. Standard electrode potential, E0. It may be measured at 25 degrees centigrade and temperature. Generally, before standard electrode potential, I can mention one sentence. The electrode potential is there. Electrode potential is generally depends upon the three factors. It generally depends upon the three factors. One is the temperature. And another one is the pressure. Another one is the pressure. Another one is the concentration. Another one is in the concentration. Sorry, this is not pressure. So this it may be the concentrations. Right? So which one it may be there? The standard electrode potential is depends upon three factors. One is temperature and nature of the metal, not pressure, because in this case we are not applying that pressure. It depends upon the so 1 molar concentration. Like this electrode potential is different, like in the earlier one, like that. See, listen. So the electrode potential generally is depends upon the temperature as well as the concentration. Which concentration? Electrolyte concentration. Concentration of the electrolyte. Whatever that electrolyte we are taking, that electrolyte concentration. And another one which is depends upon the nature of the metal. Nature of metal. Generally, the electrode potential E, not standard electrode potential, I explained that. Electrode potential E. This electrode potential E, which is depends upon the which factors? Temperature, concentration and nature of metal. These three factors mainly. So many factors are there, mainly focused, and we are focused in this particular area, these three. Now, if temperature of the system is defined, suppose temperature is specified, the temperature is at maybe 25 degrees centigrade. 25 degrees centigrade temperature, and concentration of the electrolyte, that electrolyte concentration it may be taken as 1 molar concentration, 1 molar electrolyte solution. The electrolyte solution is 1 molar electrolyte solution. 1 molar electrolyte solution, and another one is which one? 25 degree centigrade. 1 molar electrolyte solution and 25 degree centigrade. If we can measure the electrode potential, at which one? 1 molar concentration and 25 degree centigrade temperature, that potential is called as the standard electrode potential. Standard electrode potential is 1 molar concentration of the electrolyte solution and 25 degree centigrade temperature. Now, these two are already specified. Temperature as well as the concentration is specified in the standard electrode potential case. That means the standard electrode potential, this electrode potential is these three factors. Standard electrode potential case, concentration is, you know that. Temperature, you know that. Which one you know? You don't know that. Nature of the metal. That means the standard electrode potential mainly depends on which one? Nature of the metal. Standard electrode potential depends upon the nature of the metal. That means it depends upon the nature of the metal. It depends upon the nature of the metal means what will happen? Every metal has their own E0 values. It depends upon the nature of the metal. That means every metal has their own E0. Own E0 means standard electrode potential. own standard electrode potential values. That means zinc, it may be separate standard reduction potential is there, copper it may be separate standard reduction potentials are there, magnesium is like that. Any metal, you can take any metal, so that any metal, copper like that, any metal, their own E0 values, own E0, not never matched like that. It depends upon the nature of the metal. Suppose the nature of the metal, if it is zinc, if it is there, zinc plus 2 is going to be zinc. Suppose, what is this? Zinc plus 2 is going to be zinc. E0 is standard reduction potential, and I mentioned that zinc plus 2 is going to be zinc. Zinc plus 2 is going to be zinc. This is which one? Reduction potential. Or zinc is going to be zinc plus 2. This is which one? Oxidation process. M is going to be M plus N while losing in electrons. So this is which one? Standard oxidation potential. Standard oxidation potential, because E0 I mentioned that. E0 of zinc by zinc plus 2. Standard oxidation potential. How much this standard oxidation potential value is? 0.76 volts. 0.76 volts. Standard oxidation potential. And similarly, if it is Cu plus 2, while taking the 2 electrons is going to be Cu. Earlier I mentioned that. This is which one? Reduction process. So the reduction process potential is reduction potential, and this E0 is mentioned as standard reduction potential. This is what? Standard reduction potential. Standard reduction potential. So the standard reduction potential of the Cu plus 2 Cu value is how much? 0.34 volts. 0.34 volts. Now one is oxidation potential, another one is reduction potential, standard reduction potentials. Now earlier I mentioned that the oxidation potential is converted to the reduction potential, or reduction potential is converted to the oxidation potential. Suppose this is an oxidation potential, this it will be converted to the reduction potential. How? By putting the minus sign on oxidation potential. That means the standard oxidation potential is converted to the standard reduction potential. That means E0 of zinc plus 2 is going to be zinc. Zinc plus 2 is going to be zinc means what will happen? M plus N is going to be N. While taking that N number of electrons is deposited as the neutral copper or neutral solid. So that means zinc plus 2 while taking the 2 electrons is deposited as zinc. While receiving the electrons, this process is an oxidation process or reduction process. So this potential is called as the standard reduction potential. So when this is an before is which one? Oxidation potential. This will be converted to the reduction potential. What will happen? By putting that minus charge. So that means which one? Minus of oxidation potential. How much this is oxidation potential is 0.76. Before minus we can add minus 0.76 is which one? Reduction potential of zinc. Oxidation potential is converted to the reduction potential, minus 0.76 volt. That is the reduction potential of the zinc. Oxidation potential is like this. Right? So oxidation reduction potential, the conversion also takes place by putting the minus charge. One it may be given, another one. So because in the examination point of sometimes confusions will be given. One time is oxidation potentials are given and sometimes reduction potentials are given. So if you require reduction potential but oxidation potential value is given, then you can convert that reduction potential to the oxidation potential or oxidation to the reduction by putting that minus charge. This it may be happen. Standard electrode potential. Now another one, E cell is what? You know that reduction potentials, oxidation potentials and standard oxidation and standard reduction potentials, you know that. Then total E cell is equal E0 of or E of oxidation potential plus E of reduction potential. Oxidation potential and reduction potential. Right? Or E cell is equal, E0 of cell is equal E0 of oxidation potential, standard oxidation potential plus E0 of reduction potential, standard reduction potential. E0 is mentioned. So we know that oxidation process occurs at anode, reduction process occurs at cathode. Oxidation process occurs at anode, reduction process occurs at cathode, right? So before that, this oxidation potential is converted to the reduction potential. Oxidation potential is also converted to the reduction potential. What will be happen? So both, if it is reduction, one is oxidation potential, reduction potential is given like this. If both will be mentioned like this, reduction potentials, both reduction potential values is given, both reduction potentials are mentioned, E cell is equal to E cathode or E anode, E cathode minus E anode. So that means whatever the reduction potential is there, and this oxidation potential also converted to reduction potential by putting that minus charge. Minus E0 of reduction potential plus E0 of reduction potential is there. So depending upon the nature of the metals, it may be there. E cell is equal to E cathode minus E anode. E cell is equal to E cathode minus E anode is there. E cathode minus E anode. So at cathode case, which one will be happen? Reduction reaction takes place. At anode case, which one will be happen? Oxidation reaction takes place. So that both will be can explain by considering the solid bridge case like that. So it is clear discussion is there. While we can discuss the cell notation, I can explain which one is right, which one is left, what is happening in the reduction, what is happening in the oxidation like that. After we can see the cell notation. You can see the cell notation only, it clears that. Both will be given oxidation reduction potentials E cathode minus E anode. E cathode minus E anode. Or both will be given standard reduction potentials E0 of cathode minus E0 of anode. If both are reduction potentials, not one in oxidation, not one in reduction, both are reduction potentials are given, standard reduction potentials, because E0 is mentioned. Or generally we can consider it right side reduction reaction takes place, that it may be happened at the cathode. So E0 of right minus E0 of left, if both are reduction potentials are given. Or E cell is equal to E right minus E left. So at right side reduction reaction takes place, at left side oxidation reaction takes place. All it may be happen while we can see the cell notation only. Cell notation only, it will clear, your doubts will be clear by seeing the cell notation. Cell representation. Cell notation means cell representation. The total cell representation is how much? Cell representation or cell notation. How can you represent the cell notation? In the cell notation, two half cells are there. Right side of the half cell, reduction reaction takes place. Two half cells, two beakers will be taken while connecting through the solid bridge like it may be happen, and connection to the potentiometer like that it may be there. So one side it may be reduction reaction, another one half cell that it may be oxidation reaction takes place. One side it may be reduction reaction and another one side it may be the oxidation reaction takes place. So generally right side it may be a reduction reaction takes place and left side it may be oxidation reaction takes place. And these two will be separated by a salt bridge. These two are separated by a salt bridge. While considering the salt bridge, right side of the salt bridge reduction reaction takes place and left side of the salt bridge oxidation reaction takes place. This oxidation reaction is occurs at the anode, reduction reaction is occurs at the cathode. And earlier I mentioned that the standard reduction potentials is mentioned, standard oxidation potential and standard reduction potentials. That means standard electrode potentials are mentioned. So we cannot directly calculate the standard electrode potential of a particular metal. We cannot directly calculate the electrode potentials. We cannot directly calculate the electrode potentials. But we can calculate the difference between the two electrodes. We can calculate the difference between the two electrodes. We cannot directly calculate a single electrode potential. We can calculate the difference between the two electrodes. The difference between the two electrodes, which are called as which one? E cell or EMF of the cell. That's what E cell or EMF of the cell in the earlier one. Which one is given? E cathode minus E anode. If it is, both are reduction potentials. That means we can calculate the difference between the two electrodes. Difference between the two electrodes, that will be calculating the E cell value. Or E0 cell also, E cathode, E0 of cathode minus E0 of anode, like this. We cannot directly calculate single electrode potential. We can calculate the difference between the two electrodes. So suppose we can calculate the single electrode potential exactly. So another one we can imagine. Suppose we don't know given, suppose another one we can imagine, we can compare with the reference electrode. Reference electrodes. We can selecting the reference electrodes. While selecting the reference electrodes, what will happen here in this case? So one electrode is known, another one is reference electrode we can known. So reference electrode means whose electrode potential value is known. Whose standard electrode potential value is known. Reference electrode means whose electrode potential is already known. While you can comparing with the known potential value, we can calculate the difference by using the potentiometer. If it is taken in the two beakers like this, in one beaker, another one beaker, suppose this is in hydrogen electrode, dipped in another one solution. If it is suppose zinc electrode or whatever it may be electrode, if it is dipped in another one solution. So salt bridge you can add these two electrodes which are connecting through the potentiometer. That potentiometer records the EMF values. Right? So it may be burette base will be taken or whatever the electrolyte, whatever that substance will be taken, titrant, we can addition takes place. Now what will be happen? So suppose we can calculate this electrode potential. So exactly you can compare with another one electrode you can take as known electrode potential. If this potential will be known, suppose this value is known and this value from the EMF from the experiment if it is obtained, then you can calculate the required electrode potential. So that means standard electrode potential can be known, that is reference electrode. By using reference electrodes we can calculate the exact electrode potentials values. Right? So in the reference electrodes will be already standard electrode potential value is known. This value is known, that potential that is called as the reference, the electrode is called as the reference electrode. We are using two electrodes. One is the primary reference electrode. We are using. This primary reference electrode we are using as hydrogen electrode. While using the hydrogen electrode, the solution is reversible with respect to the H plus ions. After that again I can explain what will happen, in which cases we are using all, it may be explained at one place. So primary reference electrode is considered as an hydrogen electrode. So that means this hydrogen electrode which can be acts as cathode or which can be acts as anode, which is depending upon the reaction. If it is cathodic place we can use or anodic place we can use, but cathode or as well as anode. So the standard reduction potential of the hydrogen electrode value is 0 volts. Standard reduction potential of the hydrogen electrode is 0 volts. That may be primary reference electrode. Suppose if it is oxidation process takes place, so half equivalent of H2 is going to be H plus electron. This is going which one? Oxidation process. Standard electrode potential of the H2 is what? Half equivalent of H2 is going to be H plus. Half equivalent of H2 gas is going to be H plus. This value is what? 0 volts. Either it may be the reduction potential minus 0 or plus 0 is same, 0 volts. And if it is reduction reaction takes place, H plus while taking that electron, reverse process it may be takes place, half H2 gas. So this process is called as the reduction process. So this reduction potential is how much? H plus is going to be H2, half equivalent of H2 gas. So that it also be 0 volts. That it may be also the 0 volts. So oxidation and reduction as well as, that means acts as a cathode as well as anode. Reduction, oxidation takes place. So another one, reference electrodes also we are using. Secondary reference electrode. Secondary reference electrodes. That secondary reference electrodes we are using as a calomel electrode. So that means whose potential value is known already. That one is considered as the standard electrodes, reference electrodes. So the standard reference electrode, secondary reference electrode, which is considered as the calomel electrode, that reduction potential, standard reduction potential of the calomel electrode is how much? 0.242 volts. Standard reduction potential of the calomel electrode is what? 0.242 volts. So in the reference electrode of the standard reference electrode of the hydrogen calomel electrode, the representation it may be taken mercury salt which is taken, mercury paste which is taken. So the mercury Ag2Cl2 paste we can add on that mercury. After that we can passing through the KCl solution. We can passing through the KCl solution. Ag2Cl2 KCl solution we can passing takes place. This is considered as which one? When it is calomel electrode representation. I can explain in the problematic point of view clearly. Calomel electrode. Standard reference electrodes we are using as standard reference electrode, calomel electrode. Right? Ag2Cl2 we are considering that it may be the KCl. Right? So this is representation. Like oxidation reductions takes place, it may be different manner, it may be there, I can explain later. So this value it may 0.242 volt. Now this is difference between the two electrodes, it may be calculation, right? So that will be happen. So one side is reduction, another one side is oxidation takes place. Between that double vertical line is there, salt bridge is there, that it may be considered as the cell notation. During the cell notation, left side of the salt bridge reduction reaction, right side of the salt bridge is what? Oxidation reaction. Sorry, left side it may be oxidation, right side it may be reduction reaction takes place in the cell notation. Right side is reduction. When reduction reaction is occurs at cathode, oxidation reaction is occurs at anode. Right? You know that? So based on that, the cell notation, right? So how can you explain the cell notation? I can show. How can you write the cell notation? Because that cell notation is very important in the electrochemistry point of view. For the total electrochemistry, it depends upon the only cell notation. Either it may be the Nernst equation or whatever that equation which is there, that it may be depends upon the cell notation only. Is cell notation only. So cell notation. So we are using a double vertical line, double vertical line, This double vertical line indicates the salt bridge. Indicates the salt bridge. Right? This it may be the salt bridge. Right side of the salt bridge, reduction reaction takes place. This one is which one? I mentioned that earlier one, a reduction reaction. M plus N is going to take n number of electrons is deposited as the neutral metal. So charge will be neutralized. M plus N plus N electron is going to be M. That is the reduction process. I explained that earlier one, you can check them. And left side of the salt bridge, which one reaction takes place? I mentioned that oxidation. That is which one? A metal is going to be M plus N. While losing a number of electrons, M plus N plus N number of electrons are there. This is oxidation process. right? So double vertical line is indicates the salt bridge, and right side which one? Reduction. Left side it may be oxidation, right? So when reduction is happened at which one? Cathode. That it may be the right side, it may be there. Oxidation is occurs at which one case? Anode. That it may be the left side of the salt bridge. Left side of the salt bridge. So here it is single vertical line we are using. The single vertical line. What mentioned the single vertical line? Is an interface. Is an interface between the metal and its solution and its ions in the solution. Metal and its ions in the solution is an interface between the metal and its ions. Is an interface between the metal and its ions in the solution. Is considered as the single vertical line. Now what is the role of the salt bridge? And the salt bridge is a U-shaped glass tube. Salt bridge is a U-shaped glass tube like it is, like here in this type. This is a salt bridge. U-shaped glass tube is there, right? Reverted glass tube like that. U-shaped reverted glass tube or glass tube it may be there. This salt bridge is prepared in this glass tube. We can fill with the, inside the glass tube with NH4Cl or KCl or NH4NO3 or KNO3, right? So we are using this type of materials, and agar also we are using, right? So we can fill it with the salt bridge. In the salt bridge, what is the role of the salt bridge? Why we can use the salt bridge? Why we can use the salt bridge? By using the salt bridge, what will happen? By using the salt bridge, what will happen? So that means the salt bridge is connected through the two half cells. This is one half cell, this is another one half cell. So in the cell notation means complete cell. In this complete cell, right side it may be the, what is there? Reduction half cell. Left side is what? Oxidation half cell. So that means it is the, you can take like these two beakers, two cells. This is one half cell, this is one half cell. So one side it may be, which one it may be there? Oxidation. Another one side it may be the reduction, right side. So the salt bridge which is used, that it may be the connecting the two electrolyte solutions. Two electrolyte solutions we are connecting to the salt bridge. And these two are the electrodes. Suppose if it is in the Daniell cell, if it is there, the Daniell cell is an example of the galvanic cell or electrochemical cell. So we are considering the Daniell cell. Daniell cell. In the Daniell cell, so zinc electrode which is dipped in the zinc sulfate solution, and suppose if it is the copper electrode which is dipped in the, or copper rod which is dipped in the copper sulfate solution. Copper sulfate solution. And these two electrodes are connecting through the potentiometer. Now, based to the salt bridge, while using the salt bridge, what will happen? Transfer of the ions, it may be takes place, migration takes place one part to another part. During this part, what will happen? To maintain the electrical neutrality. The role of salt bridge is important one is to maintain the electrical neutrality. To maintain the electrical neutrality in the both the half cells, not one side, in both half cells. To maintain the electrical neutrality in both the half cells, we are using the salt bridge. The role of salt bridge is important to maintain the electrical neutrality in the both the half cells. How this to maintain the electrical neutrality in the both the half cells? That means transport number of cation, transport number of anion will be same. Transport number of cation, later I can explain the Kohlrausch law case, what is transport numbers, and cation transport number is what, anion transport number is what, I can explain. The transport number of cation and transport number of anion will be same. Transport number of anion and cation will be, transport numbers will be depends upon generally speeds or velocities or mobilities of the ions. So that means the mobility of the cation as well as the mobility of the anion will be same. It may be same speed, it may be takes place. The ions it may be same speed. Then transport numbers will be same. Then what will be happen? Electrical neutrality is maintained. Electrical neutrality is maintained. Later it may be this is leads to the again some additional concepts which is there, I can explain later. So junction potentials like that, liquid junction potential, again this leads to the salt bridge, it may be played a key role further point of in the liquid junction potential case, or everywhere it may be there, with salt bridge, without salt bridge, based on that these cells it may be again different types is there. So that's why salt bridge is important, right? So to maintain the electrical neutrality in the both half cells, transport number of cation as well as transport number of anion will be same. That means speeds or velocities or mobilities of the ions will be same. Right, the role of the salt bridge. Right. So this is considered as a cell notation. During the cell notation, right, if it is an example which is taken as the Daniel cell, zinc rod is dipped in the zinc sulfate and this is dipped in the copper sulfate, and you don't know which one is cathode, which one is anode. How can you consider? Either zinc is cathode or copper is cathode. Which one is considered as cathode, which one is considered as an anode? One half cell, another half cell, but connecting to the salt bridge. One half cell, another half cell connecting to the salt bridge, it is considered as the complete cell. Cell will be constructed. Now, how can you like that? You can say that whether zinc is anode, whether copper is electrode, copper is cathode. So that means if standard reduction potential value, if it is more, standard reduction potential value is more or high, that will be acts as cathode. That will be acts as cathode. Then at cathode, which one it may be takes place? Reduction reaction takes place. At cathode, which one takes place? Reduction reaction takes place, which is occurs at the right side. Next, whose electrode standard reduction potential value is low? Standard reduction potential value is low. That will be acts as anode. That will be acts as anode. At anode, which one it may be takes place? Oxidation reaction takes place. At anode, which one is takes place? Oxidation reaction is takes place. Now, I mentioned that earlier one, the standard reduction potential values of the zinc. This symbol is what? M plus N is going to be M, or zinc plus 2 while taking the 2 electrons is going to be zinc. This is what? Reduction potential, standard reduction potential. Standard reduction potential. The standard reduction potential of zinc is what? How much it may be there? Minus 0.76 volts. Minus 0.76 volt. And standard reduction potential of copper is, this is also reduction. So that's what I can explain in the earlier one. Both reduction potentials we are considering. Both are reduction potentials. E cathode minus E anode, or E right minus E left. Right? So this is also standard reduction potential. The copper standard reduction potential value is 0.34 volt. Sometimes if it is given oxidation potential, you can convert that to the reduction potential, this form. If zinc is going to be zinc plus 2 is given, which one is acts as cathode anode, so you don't confuse that value if it is mentioned as 0.76, if it is oxidation potential is given. Then again you can convert takes place oxidation potential to the reduction potential by putting that minus, that means minus 0.76 is obtained. Right? So these are two are standard reduction potential values. Now which one value is more? The standard reduction potential value is high. In which one case? Copper, Cu plus 2 case. Copper case, it may be standard reduction potential value is more, which is acts as which one? Cathode. At cathode, which one it may be takes place? Reduction reaction takes place. That means reduction reaction takes place at which one? Copper. While taking the now the standard reduction potential of the copper is more, which is acts as cathode, and standard reduction potential of zinc minus, this value is minus. When it is less, this is acts as anode, oxidation takes place. Here this value is more, acts as cathode, reduction takes place. When standard reduction potential is more, cathode, reduction takes place. Less, anode, oxidation takes place. How you can identify this? Again, these values will be examination point of view, these values will be mentioned. Standard reduction potential of zinc and standard reduction potential of copper, that values will be mentioned. Examination point of view, definitely these values will be given. No need to buy at these values. But these values is given, you can identify that whether the value is given standard reduction potential or not. You can identify that. If it is mentioned like in this format, that is reduction potential. Or mentioned like this in this format, that is an oxidation potential. So that's what reduction potential, oxidation potential is. Identification is important. So both reduction potentials, after that comparison takes place when it is more reduction, when it is less oxidation at anode. So now copper is more reduction potential, reduction reaction takes place, acts as cathode. So that means which one reduction reaction? Cu plus 2, while the taking 2 electrons is deposited as copper solid. The 2 electrons are where? How it will be generated? So now the standard reduction potential is less for the zinc, that is acts as anode. So zinc is going to be zinc plus 2 while releasing the 2 electrons. This is called as oxidation. This is called as reduction. Total cell reaction is, this is important. Total cell reaction generation is important for any reaction is cell notation. So this zinc solid, this 2 electrons is cancellation takes place, plus Cu plus 2 is going to be zinc plus 2 plus Cu solid. That it may be considered as total cell reaction. So you have an idea about the cell notation. What is a cell notation? Right? You have an idea. And which one is reduction of cell? Which one is oxidation of cell? Right side is what? Left side is what? What is salt bridge? Right? And how can you identify that? Total E cell value calculation is E cathode minus E anode. The total E cell value is how much? Here in this particular case, E0 cell value is how much? E0 cell is equal, I mentioned that earlier one. If both are reduction potentials, E0 cell is equal E0 of cathode minus E0 of anode, or E0 of right minus E0 of left. E0 of right minus E0 of left. Or E0 of right minus E0 of left. Or standard reduction potential of the cathode minus standard reduction potential of the anode. Or both will be mentioned as which one? Both is reduction potentials. So in this earlier example, this E0 cell of the earlier example is which one? E0 of the copper and E0 of the zinc. E0 of the Cu plus 2 Cu minus E0 of zinc plus 2 is going to be zinc. How much this value is? 0.34 volts. And how much this value is? Minus 0.76 volts, reduction potential. So how much this is? 0.34 minus into minus is plus 0.76. How much? 1.10 volt. E0 cell of this Daniel cell. And zinc which is dipped in the zinc sulfate, copper is dipped in the copper sulfate. Or simply, if it is any reaction is given, you can identify that E0 cell, any reaction is given, E0 cell is equal, or EMF of the cell is equal, E0 cell is equal. So I mentioned that E cathode minus E anode, or E right minus E left. At cathode, which one? Reduction reaction takes place, that is the right side. At anode, oxidation reaction takes place, that is left side, right? So cathode means which one? Highest reduction potential is there, that is acts as cathode. Lowest reduction potential is that is acts as anode. So that means highest reduction potential minus lowest reduction potential. E0 of cell is equal highest standard reduction potential minus lowest standard reduction potential. Highest standard reduction potential is what? Acts as cathode. Lowest standard reduction potential is what? Acts as anode. Right? You sometimes it may be confusion takes place. You can go for the highest reduction potential, lowest reduction. Which one is highest reduction potential? This one, 0.34. Minus, which one is lowest reduction potential? 0.76. This value is same, 1.10 volt. For E0 cell point of view. E0 cell calculation point of view. Highest reduction potential minus lowest reduction potential values. right? So next one is the Nernst equation is what? Nernst equation. Because in the syllabus point of view, Nernst equation and its related problems are there. So definitely you may imagine the question from the Nernst equation and its relations. Or this Nernst equation will be used, we are using the Nernst equation maximum in the electrochemistry point of view, or everywhere we are using that electrochemistry point of view, this Nernst equation. That's what this Nernst equation is, very important. Very important, Nernst equation. Very, very important. Because total further quantum further electrochemistry is depends upon the Nernst equation only. Nernst equation. So what is that Nernst equation will gives the relation between which one? Which factors? Nernst equation is gives the relation between which one? See, I explain that. Nernst equation. So this gives the relationship between the Nernst equation is gives the relationship between the EMF of the cell or E cell, EMF of the cell, that means electromotive force, or E cell, right? E cell, and the relation between EMF of the cell or E cell and concentration of the electrolyte in the concentration of the electrolytes in the electrolyte solution. Concentration of the electrolytes in the electrolyte solution. Right? So EMF and concentration. E cell and concentrations. So how this relation will be there? By using a thermodynamic relation. So we are using a thermodynamic relation. And we are already discussion to explain this thermodynamic relation, about this thermodynamic relation. Which one is there? Change in free energy gives free energy delta G is equal under standard conditions delta G naught plus RT ln K. RT ln K. This is the one fundamental equation is there. Right? K is what? Is a reaction constant. Right? Concentration of the products by the concentration of the reactants. Concentration of the products by the concentration of the reactants. Right? Suppose if it is a particular reaction, if it is there, A equivalents of A, small b equivalents of B, C equivalents of D, and D equivalents of D if it is there. This K value which is equal to the concentration of C, how many equivalents? Products C. Concentration of D, how many equivalents? D by concentration of A, reactants. This is A and B in B. This is considered as a rate constant like that. Right? Or reaction quotient like that, ln K. Concentration of the products by the reactants. Right? If it is given like this general reaction. Now by using this thermodynamic relation, we know that another one thermodynamic relation between the electrode potential E and free energy change. This is another one thermodynamic relation. The change in free energy and electrode potential is E or E cell. So electrode potential is E, right? Electrode potential is E and change in free energy based on these two. The relation is what? Delta G is equal minus NFE. This is another one relation is there. So if delta G is equal to minus NFE, then delta G naught is equal, standard conditions delta G naught is equal, N is the number of electrons transferred during the reaction. Number of electrons transferred. Like in the earlier one of the Daniel cell, zinc is going to be zinc plus 2 electrons, and Cu plus 2 while taking the 2 electrons is going to be Cu. That how many electrons are transferred? 2 electrons, like that. N value is 2. Number of electrons transferred during the reaction. And F is the Faraday constant. F is the Faraday constant whose value is 96,500 coulombs. And NFE naught, these two are the constant values. NFE naught, E naught is the standard electrode potential. If delta G naught, if delta G is equal to delta G naught, this E is equal to E naught. This is third equation. Equation 2 and 3 from the thermodynamic relations, we are substituting in equation number 1. This place and this place. What will be happen? Minus NFE is equal, this place minus NFE naught, minus NFE naught plus RT ln K, plus RT ln K. From this equation, if E is equal, this N minus NF is going to be right side. What will be happen? Minus NF E naught by minus NF, it is cancellation takes place, plus RT ln K by minus NF. Based on that, E is equal E naught. So here minus is there, plus is there. What will happen? Minus RT by NF ln K is there. RT by NF ln K. This is Nernst equation. This is Nernst equation. Or in another one format of the Nernst equation, E is equal E naught minus, is equal E naught minus. So in the place of ln, we are using the log. We are using the log. Which one? 2.303 RT by NF log K. If we are using log instead of the ln, it's 2.303 log base 10. Ln base E is equal to 2.303 log base 10. So just 2.303 log I just mentioned. And suppose this R is a constant, gas is constant, and at 25 degrees centigrade, and this Faraday constant, F is a Faraday constant, F is the Faraday constant. That value is how much? 96,500 coulombs. 96,500 coulombs. And R is gas is constant. And T is absolute temperature, or at T is the temperature, at T is the temperature at 25 degrees centigrade, at 25 degrees centigrade, this 2.303 RT by F value, this 2.303 RT by F value you can substitute it, and R value gas is constant, and T is substituted, right? So this value, this entire value, except N, that value which is equal to the 0.0591, which is obtained as 0.0591. Then in another one format, this equation E is equal E0 cell, or E cell is equal E0 cell, or E oxidation, only half cell will be taken, E half cell will be taken. E is equal E0 minus this value 2.303 RT by F value is how much? 0.0591 by N log K. Log K, where what is N? Number of electrons transferred during the course of the reaction. During the course of the reaction. Number of electrons transferred, N. So E0 is, you know that easily. So based on that, suppose if it is complete cell will be, suppose you can calculate the complete cell. E cell is equal E0 cell minus 0.0591 by N log K. That means for the calculation of the E cell based on the Nernst equation, what we know first? E0 cell. We know E0 cell first. Which one is E0 cell? So E0 cell, how will be calculated? In the examination point of view, standard reduction potentials of the two metals will be given. Based on that, highest reduction potential minus lowest reduction potential, or E cathode, E0 of cathode minus E0 of anode takes place. This will be happen. You have to calculate this one. And for the total cell reaction, you can obtain that number of electrons transferred easily. And K is what? From the total cell reaction, you write the total cell reaction. Oxidation is what? Reduction is what? Then concentration of the reactants products by the reactants. Then K also you know that. Then you can calculate the E cell. Suppose only off cell reaction is taken, oxidation of cell is equal E0 of the oxidation of cell plus something it may be there. E0 of reduction, E of the reduction of cell, E0 of the reduction cell, and like this it may be there. Whatever it may be, we can apply. This is the Nernst equation. Nernst equation. We can use the Nernst equation for the calculation of the E cell. The next one in the E cell, we know that in the Nernst equation point of view, if it is given only half cell is given, suppose that is an oxidation half cell is given, So how to write the Nernst equation for this? E of oxidation half cell is equal E0 of oxidation potential minus 0.0591 by N. N is how many? N electrons. N log K. Or this oxidation can be mentioned as which one? A metal is going to be M plus N. This is which one? Oxidation potential. Is equal, this is E0 of oxidation M plus N minus 0.0591 by N log K. K is what? Products by the reactants. So K is the concentration of the products by the concentration of the reactants, if it is reactants to product. Now here in this case, product is what? M plus N by M solid. This is taken in the solid form or in neutral form. M solid. In this case, electrochemistry point of view, the concentration which is taken in the solid form, that it may be very excess, it may be there. The atoms are very close distance, it may be there. Almost more concentration is there in the solid form. So that's what you can consider as 1. You can take it as 1. So that's why it may be solids form, it may be taken it as 1. Then whatever that, if it is zinc plus Cu plus 2 is glycerized to zinc plus 2 plus Cu is there. Suppose in this reaction, so the zinc solid, copper solid also you can take it as 1. That means which one? Cu plus 2 concentration, zinc plus 2 concentration by Cu plus 2 is there. Like this, here it is also, only you can consider the ions form only or electrolyte form. This it may be considered. So this it may be 1. So that means which one it may be there? Log M plus N concentration. Log M plus N. So now this oxidation potential E of oxidation potential, or this when plot takes place, suppose you can draw the plot. So Y is equal C plus mx type. Y is equal C plus mx type. In Y axis is what? Oxidation potential. In x-axis is what? Log M plus N. When intercept is there, E0 of, so that means which one? E0 of oxidation. And this negative slope which will be there, this minus sign is there, negative slope will be there. That slope is equal to what? Minus 0.0591 by N. Now based on this, when concentration of M plus N, concentration is increases, what will happen? The oxidation potential is decreases. Oxidation potential is decreases. When this one is increases, this potential is decreases. So concentration of M plus N is increases. Oxidation potential is which one? Decreases. Or this one is concentration is decreases, oxidation potential is increases. Right? Next similar one for the reduction reaction case. What is the reduction reaction? I explained that. N number of electrons, if it is absorption takes place or receiving that n number of electrons. This process is called as which one? Reduction process. Or Cu plus 2 to 2 electrons, Cu solid. Like that, in that one is zinc like that. This reduction process. So reduction half cell is equal E0 of reduction of cell minus 0.0591 by N log, which one is there? K. K it means what? Products by the reactants. Products is what? Solid. M solid. M, this is reverse takes place. M solid by the M plus N. M solid if it is there what? 1. By reactants is what? M plus N. So here it is also, you can draw the curve. Y is equal C plus Mx type. Y is equal C plus Mx type. Reduction process is which one? M plus N is going to be M. Like here in this case you may write, suppose M plus N is going to be M. And draw the plot between E reduction potential and in this case x-axis is what? Log 1 by M plus N. Or that may be changed, suppose you can also changing this. If this denominator is shifted to the numerator, what will happen? Log 1 by x is equal minus log x. Already minus is there. If it is minus log x is there, what will happen? E reduction potential is equal E0 of reduction plus 0.0591 by N log M plus N. If it is shifted to the numerator. Minus is there, already minus into minus is plus. So here it is y is equal C plus Mx type graph. On y-axis is what? Reduction potential, reduction of cell potential, and in x-axis log M plus N, and the slope is which one? Positive value with some intercept. This intercept is what? E0 of reduction, standard reduction, and slope is which one? 0.0591 by N. Based on this, what we can say that when concentration is increases, what will happen? Reduction potential is increases this direction. So the concentration of log M plus N is increases. Log M plus N is increases. What will happen? E of reduction potential is increases. This it may be increasing. Right? If it is problems will be given, suppose this Nernst equations point of view, you have to substitute that problems. Later we can see the problems. Right? In the next class we can see the problems. Right? So that's why these principles are very important. Based on this, definitely there is a question is there in the examination point of view. Or this type of reactions are, we are using the entire physical chemistry, entire electrochemistry point of view. The Nernst equation. Entire electrochemistry means in the cells point of view. So next one is, if it is given, suppose in the problematic point of view, Nernst equation and problematic point of view, relations will be given. You have to calculate the equilibrium constant. Calculate the equilibrium constant. If it is E0 cell values are mentioned, E0 cell is given, and calculate the equilibrium rate constants. That means by using the relation delta G naught plus RT L and K, you know that this relation, earlier when I mentioned that. If reaction is at equilibrium, When it is in the equilibrium, free action is at the equilibrium. When it is in the equilibrium, change in free energy is what? 0. I mentioned that earlier one. When this is 0, what will be happen? Delta G naught is equal minus RT ln K. If it is 0, delta G is equal minus RT ln K. So if it is equilibrium, this K is equal to the what? K equilibrium constant. This is the equilibrium rate constant. Minus RT ln K. So based on this, ln K equilibrium is equal to what? This minus delta G naught by RT. Minus delta G naught by RT. Then K is equilibrium is equal to what? If it is going to be right side, this is exponential factor actually. This is going to be right side exponential factor minus delta G naught by RT. This is one formula. Or you know that delta G naught is equal to what? Minus NFE. So e to the power of minus, already minus is there here. Delta G naught value is what? Minus NF E naught. Like in the earlier one I mentioned that the Nernst equations point of view, delta G is equal to minus NF E, delta G naught is equal to what? Minus NF E naught. You know that. So that will be substitution takes place by RT. What will be happen? K equilibrium is equal exponential factor, minus into minus is plus. NF E naught by RT. N value, E naught value, you can substitution takes place, that will be obtained. This is one type of formula. Or from this formula, delta G naught is equal, what we can write in place of ln, we can substitute log, suppose 2.303 RT log K equilibrium. Suppose delta G naught is equal minus NF E naught log K equilibrium, and this minus is cancellation takes place, right? So what will be happen? Log K equilibrium is equal NF E naught by 2.303 RT. And earlier we know that 2.303 RT by F value at 25 degrees centigrade. Earlier I had mentioned that at 25 degrees centigrade or 298 Kelvin, 2.303 RT by F is equal to how much? It may be there 0.0591. So now this is reverse if it is there. F by 2.303 RT. That means which one? 1 by 0.0591. So that is equal to what? N E naught. This is what? F by 2.303 RT is there. Reverse if it is there. So that means 0.0591. Reverse if it is takes place. So this is log K equilibrium. Then K equilibrium rate constant you have to calculate. So this log, it may be going to be right side, log base 10 is there. Log base 10, ln base E. Ln going to be right side, exponential factor. Log it may be there 10. 10 to the power of N E naught by 0.0591. So what is E naught? E naught cell. E naught is what? E naught cell. E naught is E naught cell. You have to calculate that E naught cell. How to calculate that E naught cell? E naught of the cathode minus E naught of the anode, or highest reduction potential, highest standard reduction potential minus lowest standard reduction potentials. This is one way if it is examination point of view, based on this type of questions also there, right? This methods also questions will be framed. So the regulations is there in Nernst equations point of view, so that's what I can explain here in this case. So in the next class we have seen the problems. So which type of problems may be appears in the examination point of view, like this Nernst equations point of view. Purely Nernst equation. Next one, sometimes the problems will be given. Which type of problems? Suppose if a reaction will be given A plus N1 number of electrons if it is absorption takes place, suppose B is formation takes place. The standard reduction potential if it is given E1 naught, standard reduction potential is E1 naught, standard reduction potential. And second reaction if it is given B, this product B will be taken, N2 number of electrons which is absorption takes place. Suppose C is the product. During this reaction, E2 naught is the standard reduction potential. In the third step which is mentioned, suppose this reaction it maybe takes place by the A is absorption takes place by the N3 number of electrons. Directly C is there. What is E3 naught? What is E3 naught? This type of questions are there. So that means A to B and B to C takes place, but which is mentioned as directly A to C. Which one is the E3 naught? You have to calculate. So earlier I mentioned that delta G is equal, if suppose this is delta G1, this is delta G2, this is delta G, suppose this A to C is equal. Or delta G3, this one. Delta G3 naught is equal delta G1 naught plus delta G2 naught. Why? Because this is A to B and B to C takes place, direct A to C is there. That means by using these two, this will be generated. So delta G naught, D1 naught plus delta G2 naught. So you know that delta G3 naught case, N3 number of electrons are there, F is the Faraday constant and E naught 3 is the standard reduction potential or electrode potential. This is because reduction reaction is given, reduction potential I just mentioned. And here in this case, which one? Delta G1 is N1 number of electrons, F into E1 naught. And this one is what? Delta G naught, G2 naught, N2 number of electrons and F and E2 naught. Why? Because it is delta G is equal, delta G naught is equal minus NF E naught. This formula is there. Or delta G is equal minus NF E. E is electrode potential like that. Right? Delta G is free energy change and is number of electrons transferred. Here N1 number of electrons transferred, here N2 number of, here N3 number of electrons transfer takes place. By using this, suppose if it is minus F is the common, which one? N1 E1 naught plus N2 E2 naught is equal, here in this case I can explain this is N3 E3 naught, this minus F is cancellation takes place. Then E3 naught is equal to what? N1 E1 naught plus N2 E2 naught by what? N3. This type of formulas we are using, we are calculating E3 naught values. This type of questions also there in the examination's point of view. There is a chance. There is a chance to asking this type of questions also. Right? If it is given like this also, we have to solve this. This is one type, it may be there in the examination's point of view. So in any one case, suppose if it is given, I already mentioned that standard reduction potentials, how to calculate that. Suppose I can given that. So for the Nernst equations point of view, for the calculation of the E0 cell is important first. Suppose I will given, suppose E0 of zinc plus 2 zinc is given, suppose minus 0.76 volt, and E0 of Cu plus 2 Cu is given 0.34 volts. And what is E0 cell for this reaction? And second one, suppose if it is mentioned, I mentioned that .80 volts, sorry, 0.34 in the copper, in the silver is 0.80 volts. 0.80 volts. What is E0 cell value? First, whatever that the problem in the Nernst equation will be given, E0 cell will be important, calculation of the E0 cell. That's why E0 cell it may be very important. I can explain in the Nernst equations point of view clearly why E0 cell is important. So how much E naught cell here in this type of reactions? How much is the E naught cell? You have to calculate the E naught cell for this type of reactions. Suppose another one example, if it is given. And suppose E naught of what is E0 cells for this type of reactions? I mentioned that you can compare the reduction potential. First, reduction potential values are given or not. All are reduction potentials. Reduction reactions. All are reduction potentials. M plus N by M. That means reduction potential values are mentioned. So you can compare that. Highest reduction potential is which one? Here. This is lowest reduction potential. Highest reduction potential is cathode, oxidation, reduction takes place. Lowest reduction potential is oxidation takes place, acts as anode. So for the calculation of the E0 cell, which one formulas I mentioned that? E0 of cathode minus E0 of anode, or E0 right minus E0 left, or highest standard reduction potential minus lowest standard reduction potentials, or E0 of cathode minus E0 of anode, or E0 right minus E0 left, any one it may be there. Highest reduction potential is acts as cathode, this one, 0.34, and minus of lowest value is how much? Minus of minus 0.76. So 1.10 volts. Now this example, only E0 cell, not E cell. E cell from the Nernst equation. E cell is equal E0 cell minus 0.059 by N log K. That one we are using for other point of view. Concentrations also given. Reactions also mentioned. Now here in this case, which one is acts as cathode, which one is acts as anode? This is highest reduction potential, acts as cathode. This is lowest reduction potential, right? This is acts as anode, right? So highest reduction potential minus lowest reduction potential, simply minus lowest reduction potential. So how much it may be there? Nearly this value, it may be the 4.6 volts. Now in these two cases, E0 cell is how to calculate. E0 cell is equal highest reduction potential minus lowest reduction potential. Now both will be given minus values. Which one value is more? This value is more, acts as cathode. This value is less, acts as anode. Highest is what? Minus 0.25. And lowest is what? Minus 0.44. Highest reduction potential minus lowest reduction. So that means what? Minus 0.25 plus 0.44. How much it will be there? Nearly 0.19 volt. 0.19 volt. Sometimes it may be given oxidation potentials are given. Instead of this Cu plus 2 Cu, suppose is given Cu by Cu plus 2. Here minus sign is mentioned. Then you can convert to the reduction potential. That means we can add again minus, this it may be happen. Right? I can explain in the problematics point of view while seeing the Nernst equations case. Clear discussion takes place in the problematics point of view. Right?